Section 13.3, Geometric Probability. Hey friends, we're going to get started with this lesson. New vocabulary, geometric probability. What is it? It really is exactly what you think. It's the probability that's going to be used anytime we are considering geometric objects in our probability. For instance, we can consider the segment AB and figure out or think about what's the probability if things or dots were or darts were randomly thrown at this line and it was equally probable a segment and it was equally probable to hit any of the points from A to B. What's the probability of it being on CD? And so that would be one example. Another would be something like if you had this circular game board and I'd give you the radius and I'd say, what is the probability of a dart thrown at this circular game board that it falls in a space that is prime number or something? And so you'd have to calculate the area here, the area here, the area here, the area of all the prime spaces, and then add it up and blah, blah, blah. So those are the things that we're going to be talking about with geometric probability. And here is the first one that we can talk about. And I think a lot of this is very straightforward. Like you would get it if I didn't talk about it, but I'm going to talk about it anyway, just to make sure the concepts are solidified. So here you have very similar to what I drew. If a line segment won the whole thing, if you have this whole line segment and you draw another line segment on it, the probability of something falling on that line segment that's on it is going to be the length of the smaller line segment over the entire line segment, or in exactly BC over AD, the length of BC over AD. And so that brings us to our first example, which is straight up out of the out of that situation. Point X is chosen at random on JM. Find the probability that X will be on KL. So it's going to be the length of KL, 7, over the length of the entire, so it's KL, let me write it down like that, over JM. So the length of KL is 7, and the entire length here is going to be 14. So 7 out of 14, or 1/2. The probability is that any point chosen at random between J and M will be on KL. So in this next example, we're considering the idea of a train and your wait time. So I want you to observe down here, the Chicago Transit Authority, a Chicago Transit Authority train arrives or departs a station like Addison on the red line every 15 minutes. And here's our question. We're going to use that information at the left, and we're going to assume that we're arriving at Addison on the red line at some random time. What is the probability that we will have to wait 5 or more minutes for a train? So what we're going to do is a visual representation. So if I use this number line as a representative of how many minutes you have to wait, it makes sense that the maximum number of minutes is 15 and the least number of minutes would be 0. So basically, if you are coming to at a random time to wait on a train, you're going to be coming somewhere from 0 to 15 minutes of wait. And so the question they asked us was, assuming that you arrive at the station at some random time, what is the probability that you will have to wait 5 minutes or more? So that means the time that we're concerned about, or in a sense, the segment that I'm kind of concerned about, if you want to think about it that way, it would be from just after 5 minutes, well, at 5 minutes or above. So that's really not punctuating that right now. That color's not bright enough, to be honest. I need to do it like this. Boom. Okay. So this is the segment that we're trying to figure out what's the probability that we're going to be on this part of the segment. So you guys get it already. The length of the entire segment is going to be like my all possible outcomes. It would be 15 possible outcomes in a sense. And the values up here would be from 5 to 15, or that length would be 10. So 10 out of 15, or a 2/3 probability of me actually having to wait 5 or more minutes. As we mentioned earlier, when we talk about geometric probability, we're also talking about 3D situations. Not 3D. Well, I guess you could do 3D, but that's not what we're talking about. We're talking about 2D or area situations when you want to talk about the probability of hitting this circular section. If it's equally probable that you can hit any place in this rectangle, it would be the area of the entire thing as the denominator, and the numerator, or the thing that you really want, would be the area of the top, or the smaller section, or I should say, as we're thinking about it in terms of probability of the desired section, right? So area of the total section at the bottom and at the bottom and the area of the desired section at the top. So we're going to suppose the skydiver must land on a target of 3 concentric circles. If the diameter of the center circle is 2 yards and the circles are spaced 1 yard apart, what is the probability that the skydiver will land in the red circle? And this is assuming that the skydiver will land on the target, but what's the probability that they'll land on the red part of the target? So if I want to get a visual on what's going on, I need to first kind of draw a diagram myself to represent what's happening. It says the diameter of the center circle is 2 yards. If the diameter is 2 yards, then the radius is 1. But then as we go out further, each of these would be 1 yard. And yes, I know I didn't draw a very good picture, but this is our situation. So the diameter of the larger one would be 6 yards. This medium yellow circle would be 4 yards, whereas the diameter of the red circle is 2. So what we have to find is the area of the red circle over the area of the entire circle, which the entire like bullseye, which will be the area of the blue circle by itself. Make sense? All right, so let's go ahead and start calculating. Area of a circle is going to be pi r squared. This one is going to be pi 1 squared because the radius is 1, so it's basically going to be pi, right? Pi yards squared. And the area of this bottom circle where the radius is 3 is going to be 9 pi. And so since the area of the top over the bottom, we can reduce it, right? And get 1/9. So the probability of the skydiver falling exactly on that red circle is 1/9. The probability is 1/9 basically, which is just about 11%. So here's example 4. It's our last example of the section. We're going to use measures to find geometric probability. So if you notice, our spinner circle here has degrees. So this will be 45 degrees, 90 degrees, 50, 70, and 105 degrees, referring to the color, how much color is how much of the colored sector is taking up of the whole entire 360 degrees of this circle, right? And so what's the probability? So we're going to find some information. We're going to find the probability of each of the things. What's the probability of the pointer landing on the yellow portion? So that would be 45 degrees. That's the yellow portion is 45 degrees out of the entire 360. And we can reduce that, right, to 1 out of 8. So 1/8 is the probability of it landing in the yellow section. How about the landing on purple? I'm going to assume this is purple, though my screen is not capturing it as purple. But for today, it's going to be purple. It looks burgundy to me. But 105 out of 360 can also be reduced. I'm trying to think about how to do that on the fly. 5 goes into that 21 times. And how many times does 5 goes into this? 72 times. Let's see, I think you can be reduced some more. Let's try 3, 7. 3 goes into this 24 times. So 7/24, or 7 out of 24 would be the probability of the pointer landing in that purple section. And finally, this last one, the pointer landing on neither red, so not this section, or on blue. So we could calculate the probability of the pointer landing there and then subtract it from 1. Does that kind of make sense to you? Because we could think about, okay, the probability of it landing somewhere here is 1. The probability of it landing here would be whatever we calculate. And then therefore the probability of it landing here would be the difference. I'm going to write it that way. So 1 is the probability of it definitely happening. And I want to subtract the probability of red or blue. And when I do that, I'm expecting to get the probability of red nor blue. No red or blue. Let me write no. No red nor blue. Okay? And so 1 minus, what's the probability of red or blue? 70 plus 50 is 120. So that will be 120 over 360. And I'll continue to reduce that by saying that's really 1/3, right? Because that's 12 over 36, which can be reduced down to 1/3. And so I should write 1/3 and not 1/2. And so we have 1/3. 1 minus 1/3 is going to be 2/3 because that's like 3/3 minus 1/3 is 2/3. So you have 3/3 of 2/3 of a probability for it to land elsewhere aside from the other two. You might be asking the question, why do we do that? Couldn't we have just taken 105, added 45, and then added 90 and gotten 240 and 240 over 360? Absolutely. Same thing. Just wanted to talk about a different way to get to the answer. So either way, even if you had done the probability of all the other colors. So I'll call it purple again, but I don't agree. Probability of purple or yellow or green, right? If you had added those up, we would have gotten 240 out of 360, which becomes exactly the same thing. 2/3. All right, with that in mind, guys, that's it for us. That's it for this lesson. Let me know if there's any questions, and I look forward to talking to you soon, all right? Take care, sweeties. Bye-bye.